Hello. Today, our first question is give the state diagram for a deterministic finite automata recognizes. We have here V is epsilon or starts with B or starts with AB over the alphabet. Alphabet, what is our alphabet? A and B. Uh, Here we have three important points in this question. Uh, we can start epsilon or B or add AB. Uh, in this question, we will try the draw state diagram. Let's draw it. Uh, the deterministic finite automata has four states in this question. Q0, Q1, Q2, Q3. And we will have three accepted states. Why three accepted states? Because I said we can start epsilon, B, and AB. Uh, for example, in here B, BA, BB, okay, BB, and BBB, blah blah blah. And also AB, we can start AB, okay, ABA, blah blah blah. Uh, okay, I said we have Q0. We have Q0. I will draw two circle. Why two circle? Because this is a capted state for epsilon and Q0 our initial state. And then I will draw Q1 here and I am also draw two circle. This two circle means a capting state. Uh, this capting state for strings starting with B. How? Starting with B like that, like this. Okay, starting with B. Okay, Q0, Q1, and the other one is we have Q2. In here, I just draw one circle. Okay, and intermediate state. This is intermediate state for strings start with A. Starts with A. Okay, and we have Q3. Okay, and I'm also drawing two circle. Why? Because we Q3 is capting state for strings with AB. How? Okay, this is the initial state, right? We are starting from Q0 and transition Q2 and Q3. This is a B. Okay, AB. Okay, this is a AB. Okay. Uh, Now Q we will connect Q1 and Q3. What is the uh, alphabet here? Uh, A and B, both of them true, because we starting B, we can write BA, BB. We can write both of them, and then here A and B. Uh, if we start think AB, we can write ABA or ABB. Okay, this is my uh, state diagram. We have here K transitions. What is the uh, three K transitions here? Firstly, Q0 to Q1, Q0, Q0, Q1. This is a on B. Okay, Q0 to Q2 here on A, Q2 to Q3 on B here. These three red lines are K transitions. States Q0, Q1, and Q3 are accepting states here. These DFA, deterministic finite automata, kept empty strings here, empty strings, and the string starting with B here, and string starting with AB here, thus correctly recognizing the given language. Okay, this is our answer of the question 1. Okay, second question. Describe the language represented by the automata below. Specify exactly what set of strings it accepts. Briefly explain why the DFA accepts this set of string. Now, first let's examine the automaton. The start state. Our start state is starting point. Starting state is A here, and it's also a captured state because it has two circle. If state has two circle, it will be a capting state. And also I have three states A, B, and C. And between these, I have A, B, B, A. These are transitions. Okay, let's analyze the transitions. For example, from A to B, my transition is A. From B to B, my transition is A. And from C to B, my transition is B. Okay. And let's determine the capted language because it wants from we a captive language here. A captive language since A uh, is the capting state. The string is a capted when it is empty or when we return to A. When it is empty or when we return to A. And to return to A, we must use even number. What is the even number? 0, 2, 4, like that. Even number of B's while passing through B. We must use even number of B's while passing B. Okay, now definition of the captive language. Empty string. Firstly, empty string. What is the empty string? Here. And to return to A, string starting with A. Here. And B here. And A. We set starting with A, okay, and we must use even number of B's. Here there are two B and any of A's. Here I have one A, okay. This is empty and these are both of them our definition of the captive language. Okay, explanation. A is the start and the captive state, we said. So the empty string is a captive. Empty string is a captive. A transition to B. A transition to B. From B to C with B. Uh, from B to C here B. And from C to B, B, both of them. This allows for an even number of B's. Okay. B to B with A allows for any number of A's at the end. In conclusion, the language captured by the DVA can express it as I can try write the answer empty string here and union and starting with A and 2B even number and any of A here and n bigger than or equals 0 here. This is the answer. I tried the right. Okay, this is the answer of the second question. Okay, this is answer of the third question. Now I will explain how we can draw. Firstly, Q0, Q1, and Q2, we have three states. And Q0 is our initial state and capting state because Q0 has two circles. And now we are seeing transitions A and B, and B also our alphabet. Uh, our alphabet contains just A and B. And first, let's understand the language. Uh, language L. Language L. Uh, the empty string is kept it as it is not A. It is not A or B and doesn't contain A B. Single character strings A or B are not kept. No string containing the substring AB is kept. Okay. Uh, Actually, it is our answer. This is the answer of the third question. State diagram. Okay. Okay. Now, fourth question. Describe the language represented by the automata below. Specify exactly what set of strings it kept. Briefly explain why the DVA kept this set of strings. Now, uh, let's analyze the DVA. Uh, in this diagram, we have two accepting states. One of them 3, one of them 6, because they have two circles. These are double circlet and accepting states. Now examine the valid paths. For example, 1, 2, 3, 0, 0, and 0. 1, 2, and 3. Okay. This is valid paths 0, 0, 0, 1, 2, 3. Okay. First, one of them is second. 1, 2, 3, 4, 5, and 6. 0, 0, 0, 1, 1, 0, 0. The other one is 0, 0, 0, 1, 1, 0, 0. This is 1, 2, 3, 4, 5, 6, 7. Okay. The other one is, the other valid paths is 1, 2, 3, and 3. This is a 1, 0, 0, 0, 3, and 3, 0. 0, 0, 0, and 0. 1, 2, 3, 3. The other valid paths 1, 2, 3, 4, and 4. Here 0, 0, 0, 1, and 1. 0, 0, 0, 1, 1, and blah blah blah, because it can go. It can contain. Okay. Now, can loop with 0 uh, after state 3. Can loop with 0. Can loop with 1 state 4 here, and can loop with 0 after state 6. Now, a captive language L. A captive language is 0, 0, 0, and 0. and 0, 0, 0, 1, 1, 0 and 0. This is our encrypted language. This means strings starting with 0, 0, 0, 0, 0, 0, okay, starting with it, followed by any number of zeros, or strings starting with 0, 0, 0, 1, 1, 0, followed by any number of 0. And between this 0, there are two 1. This means in the second question, we must use, we said we must use uh, even number of 1, or A or B. Uh, this is a captured language. Uh, so I'm starting with zeros, and I am using even number of ones, and I'm also contain the any number of zeros. This is a captured language. The DVA accepts this language because it must start with at least three zeros. It must start with at least three zeros. After state 3, it either caps or goes to state 6 by adding 110, 110. In states 3 and 6, additional zeros can be added and still be kept. Therefore, this DVA recognizes and caps strings with these specified characteristics, defining the described language. Okay, this is the answer of the question. Okay, now it is fifth question. Okay, what is the fifth question? Give the state diagram for a NFA that recognize WAB we contains at least one instance of BA or this. Uh, Now I drawed s- state diagram. I'm not sure it is true or not. Uh, I tried to draw. Uh, let's understanding the problem uh, in this question. Uh, we here, what is the means here? That string v consists of any sequence of the characters a and b. Our NFA should accept any string that contains at least one uh, of BABAB or ABBB or BBBBB. At least that contains at least one. Okay, designing NFA states. Okay, states. Let's show. We need states to track each of the strings B, B, A, B, A, B, A, B, 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 or B, 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 B. Well, create transitions for each substring separately. Yes, we created transitions for each substring separately. Start state here, the initial state will be a state from which we can begin tracking and any of three substrings. Final states, once we recognize any of three substrings B, A, B, 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 A, B, A, B, 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 we reach an accepting state. Okay, transitions. Since the NFA needs to handle multiple substrings, it will branch into different transitions based on which substring we are trying to recognize. For example, for the substring BAB, we will have six states, right? One, two, three, four, five, six states. The start state here and a state for each character of the substring. Yeah. This NFA is designed to recognize any string that contains one of the specified substrings by transitioning through multiple states that corresponds to each character of the substrings. The NFA branches non-deterministically to check for each substring independently. Okay, answer the question of fifth and state diagram of the fifth question. Okay, thank you.